Hi again, everyone. We'll continue from last time. Today's class will talk about silicon as a semiconductor, some information about the clean room and particles. I mentioned some of them last time. We'll talk deeply into yield, what it is, what it means, how it's measured, what are the different kinds, and e-test, which means electronic testing. We'll talk about assembly and reliability. We'll talk slightly about design and process interactions, and we'll end with the future trends. I will also take the opportunity to do another process flow, more brief one, but a two-dimensional versus the one-dimensional I did last time. And I have a few samples to show you today. Okay, please stop me for any questions. So first, silicon as a semiconductor. 95%, actually much more than that, of the semiconductors today are silicon. There are some other few semiconductors used for other things, some specific circuits, infrared detectors, power circuits, radio frequency, lasers, and so on. But mostly, actually, out of the revenue, almost everything is silicon. There's no substitution for silicon today. Yes?
It's only for microprocessors, right? For LED and stuff? For light?
No, actually, when you look at the volume of all microprocessors from a money point of view, almost everything is made of silicon. By the way, even LEDs today are being made on silicon. So they grow gallium nitride onto silicon substrate. So almost everything is coupled onto silicon. Even lasers today are made on silicon. There's tiny indium phosphide pieces which are bonded into silicon, and all the rest is done on silicon. So silicon is the basis, and off silicon there are many kinds of combinations with germanium, with carbon, with other stuff, with additions of many things. Okay, the reason for silicon being the lead semiconductor, historically germanium was the lead semiconductor, but silicon took the lead because of the interface between silicon and silicon dioxide. That interface made it the easiest semiconductor for MOS capacitors, for MOS transistors, and actually made it very easy for processing. Germanium doesn't have that kind of oxide interface. The oxide interface is measured by the number of charges or number of traps. And for silicon, it's a very low number. Actually, this is not even the best number. Silicon is made currently on 6, 8, and 12 inches. I brought you an example. So this is an 8-inch wafer, about 200 millimeters. And this is a 300 millimeters or a 12-inch wafer. These are actually out of production lines. These are made in factories today, and the parts are being sold. Right now, there are plans to make the wafers even bigger. But although the wafer is all made of silicon, the thickness is it's less than 1 millimeter, about 700 micron, depending on the wafer diameter. When the wafer is bigger, the silicon is thicker just to support it mechanically. But although there's a lot of silicon, all the active area is about the 1 top micron of the wafer. Now I have a question for you. Why do we prefer to run silicon on a 12-inch wafer instead of an 8-inch wafer? Why is it better to do it on this wafer than on this wafer? Yeah, so more chips on the same time. So when we take the wafer and do some kind of deposition, here we can deposit, say, 100 chips, and here we can do about 230 chips. Okay, now all the processes which have edge issues, there is more edge on this wafer than on this wafer compared to the non-edge area. Okay, more edge. Now, there's one thing which is not being done on all the wafer at once. What operation is being done very selectively on what? Lithography. And why is that? For lithography, very few processes can use one mask for all the wafer. Very, very few. Actually, I know of such processes in 8-inch. I don't know of any such processes at 12-inch. And the reason is the mask, we want this is an example of a real mask made of quartz. So the mask, I'll put it here so you can see the reflection. The mask contains 4 chips. Now we produce 4 chips at once, and then we print 4, and then we move, we print another 4, and then we move, we print another 4. The reason is that we want each time we print to be properly focused. And if we print all the wafer together, it won't be focused well as it can be with one mask with very few chips. Now, you can see the chips on these masks. There are 4 of them. So each one looks this big. What is the real size in reality? It depends on the magnification. Actually, there's a reduction, and the reduction is either 1:4 or 1:5, depending on the tool, and then we get chips about this size. You can see here a few chips on the wafer. Okay. Now, one nice thing to see with the mask is the density of the lines. There are many, many, many lines. Now, a way to see that there are really lines is to see the diffraction with the laser. So this is a laser, this is a mask. There are many lines, and I'll try to... Can you see the diffraction on the board? Okay, so it moves from horizontal to vertical depending on the structure I'm lighting. Okay, so this is a mask, and although the photolithography is done one mask at a time, we call it a frame, one frame at a time, and it takes longer to cover 300 millimeter. Except for this step, all the other steps are done on the wafer as a whole. And then it makes it much cheaper to produce a 300 millimeter or 12-inch than a 200 or an 8-inch wafer. Okay.
Why are there so many lines?
The lines are, when you see a lot of lines, it's usually the memory part of the processor. So the logic of the processor is, I can't say random, but looks more random than the lines themselves. The lines are very ordered and usually associated with a memory which is repeatable. Okay. So the clean room itself, we talked about it. It's the physical manufacturing area. We don't spare any money in order to make the clean room clean. And the reason is that every extra defect kills a die. So every dollar we spent in cleaning the clean room saves us a lot of dollars in output of dies. Particles as small as 50 nanometers. This is 0.05 micron. can kill, and actually are killers. In today's technologies, even smaller particles can be killers. And the reason is, when you're trying to print a line which is 50 micron, if you have a a line which is 50 nanometers, if you have a particle which is 50 nanometers, it could completely block the line, make it an open, or short two adjacent lines. So a particle of the same size of the lithography node, the half pitch of the lithography, is a killer. If it's smaller than that, it could be a killer, but most probably it could be a reliability problem, and we will talk about that later. So as we said, the clean room is measured by classes. The clean room is a class 1 area, which means one or less particles, size 0.3 microns. Now, you already heard that 0.3 is not good enough, that even smaller particles are killers. And it is 10,000 times cleaner than a hospital operating room. Now, what happens today, since it's too expensive to clean the whole clean room, and actually it's not clean enough, what we do is, for the tool itself, we have a mini environment which is even cleaner than the clean room itself, okay? Which is cleaner than class 1. Just to show you the sizes. So the blue area is a cross-section of a human hair, between 75 and 100 microns. Depending if it's blonde, it's a bit smaller. If it's black, it's a bit thicker. Red hair is the thickest. And this area, the yellow area, is about the biggest particles the eye can see. Okay, we can see particles which are smaller than the thickness of a human hair, but not by much. And this one is a particle. When I started teaching this course, this was a killer particle. Today, this is bigger than 10 times a killer particle. So you get an impression of how big are the particles. So now I just talked about this one. So this is a human hair under a microscope on top of a wafer. So you can clearly see that one human hair on top of a wafer will kill quite a lot of circuits. So there's no way we can allow not a hair, not part of a hair, and not even a particle 1,000 times smaller than a hair to be on the wafers. How do we detect that? Here I used a material from applied material explaining what is a bright field and what is a dark field. So where this is the wafer. Sorry. This is the wafer. Now, here is a defect we want to see. This the star here. Okay? And okay, this is the defect we want to see, and what we do is we use a light, usually a laser, to illuminate the wafer itself. Now, assume this is the laser, and it illuminates the wafer. It scans the wafer line by line, or die by die. Okay, and when it reaches a particle, what do we see? The particle scatters light. The light that is being reflected directly is what is collected in a detector, and is what we call a bright field detection. And this detection is sensitive to slow variation over large areas, thickness variations, color variations, which are byproduct of thickness variations. we can also get a good picture of what we're looking at because we illuminate it. Now, if this is a particle, it will reflect the light also to other places. And then, in other directions, the light collected is called dark field detection. And dark field is sensitive to small defects, sharp edges, corners of structures, and so on and so forth. Now, we show here just one detector, but obviously you can have several detectors. And this is a very good way to catch very small particles. The signal to noise is very good. What is the signal to noise? The ratio between the light we get from the background, and for bright field detection there's a lot of light from the background because the reflection is always there. So the background for dark field is very low, and the signal is relatively high. There's a reflection from a corner. So the ratio is better than the ratio for bright field detection. Yes?
Every process, every chip will go through this phase, or it's just randomly checked, like one in 10,000?
So this depends on the fabrication facility and the exact methods. And at several steps in the line, the wafers will be checked. Usually, just a few wafers from the lot. Say a lot has 25 wafers. Rarely more than 5 wafers will be checked, typically between 1 and 3. If the tool that is being used, for example, an etch tool, has 2 chambers, so it's enough to check the first 2 wafers, because one reflects the particle from one chamber and the other the particles from the other chamber. So if suddenly one chamber goes bad, it's enough to measure 2 wafers in order to check that. So it depends on the capacity of the inspection tools, the cost of the inspection tools, and so on. We try to maximize to get the maximum detection for the cheapest price. When the technology is very young, there are lots of particles, there are many things that are not certain. There's a lot of detection, a lot of tools, a lot of inspection. While when the technology is running in production at high volumes, usually we keep the same amount of tools we bought initially for the technology, and we use them for 10 times the amount of wafers. So we use less and less detection. Yes?
What kind of effects can it reveal?
Good question. So one option is to detect a process which was incomplete. For example, we look at this die, and these contacts, these are holes which are supposed to be contacts, are not good enough. They're not, you see, they're different from the black ones. They're not etched all the way. Now, how would we know that these are bad contacts? One way is to memorize the picture and compare it to the memory. But this is not that easy, because sometimes there are slight variations, and then the memory looks a bit different. So what we do is we compare one die to the other. And if comparing the 2 dies, we see a difference, then we say it's a defect. So we get a reference die, and we compare to it. Okay? So reference die on the same wafer. Other kinds of... It's not done randomly. There is an order, and it's being optimized depending on the process, on the wafer, usually. So it can be done for all the dies in the wafer. That's usually the case. But even in a die, we don't check all the area in the die. For example, sometimes we look in the memory areas. Sometimes we look in some other sensitive areas, which are more dense. We're looking for the particles in certain areas. Why don't we look everywhere all the time on all the wafer in every operation? Because it takes time, which costs money, because it costs more tools. So we try to optimize the scanning. Other kinds of defects. So here you can see a defect, which is some metal residue here on top of the 5th metal layer on the process, and you can see it ruins it, potentially shortening it to another line. Here you can see another particle. This is a silicon particle. This is a cross-section of the silicon particles, and you can see that it is bridging between two metals. This is actually the worst case, because bridging between two metals could be, if the silicon is conducting, it would be a short and it would kill the die. But if the silicon in these conditions is close to intrinsic silicon or very low doped silicon, it might not short the metal lines. But then at the customer, it might get heated, get better conduction, and then short the metal lines. So you buy a new cell phone, and then after a few times it stops working because of such a particles. And we will talk about that. That would be a reliability problem versus a short done by metal, which is a quality problem, which is killing the die, but you can check it immediately. Okay, next chapter, yield and electronic testing. Electronic testing, or for short, e-test. I will mention yield, basic MOS transistors, and the devices and e-test structures. So first, the terminology. What is yield? Yield is the ratio between what we produce and what is actually good production. So if, for example, we look at the line yield and we get 100 wafers inside the line, but a few wafers broke inside the line, a few wafers got too many defects and we decided not to continue them, a few wafers got to sorting, and then we found out that one layer is missing, so we need to throw them away. Eventually, the number of wafers out of the fab divided by the numbers of wafers in is defined as the line yield. The wafers out could be 97% of the wafers in, okay, 95%, 99%. It depends on the quality of the fab, the performance of the fabrication facility, and it also depends on the complexity of the process. A process with very few layers in an old technology is expected to have a very high line yield, about 99%. Wafer with the new technology... No, not that much. No, because every now and then you get a wafer that gets broken. Every now and then a tool stops running while a wafer was in process and we have to throw the wafer. So every now and then you have mistakes and issues and you throw a wafer. So 99% is an excellent result for line yield. Yes?
But it depends on how many chips are okay on this equipment.
So now we're going to what is die yield. So how many wafers get out is the line yield. Now, on every wafer, we have the amount of good dies out of the total dies printed. So if we print 1,000 dies, but only 500 of them are good at end of line because the rest had particles or some systematic issues, then this is 50% die yield. And what you can see here on this wafer, you can see that several dies were taken out. These were the dies which were taken out were the good dies. We used them. Actually, some other dies here are good, but this is an example. Okay? This would be considered a very low yielding wafer, right? About 30%. Okay? This, which is a state-of-the-art process, I won't mention the process and the product because of confidentiality issues, but you can see a very good die yield, better than 90%. Okay? and this is an advanced process with an advanced product. Some of you might have it on their discon key. Okay? So this is a very high line die yield. This wafer, by the way, was produced by Micron. Okay, so now we have the definition of line yield and die yield. Now, the total yield out of the fab is the total potential number of dies we can get out, and is divided into several yield mechanisms. So, the total yield of the fab depends on the line yield and on the die yield. Now, the die yield itself depends on two separate mechanisms. One is die yield S, which is the systematic die yield, and the other one is die yield R, which is the random die yield. What is the systematic die yield? Systematic die yield appears when the process is not mature enough. It's not completely ready for manufacturing, or it's ready for manufacturing but not at high volume. For example, we have some systematic problem in the process, and sometimes the etch does not open the contacts completely. So it's not just one contact which is not open, but there are many contacts which are not open, and they're not only on one die but on several dies on the wafer. So if we have a systematic problem, it could reduce the yield by several percents. Okay? Now, when the process is mature, the systematic die yield goes to very close to 100%. But still, there's a random element. The random element means, and here you can see this is probably a random element. Every now and then, we get a particle which kills a die. So the random yield is usually actual particles. So when we look at the random yield, we see that there is a dependency of the random yield, random die yield, on the die size. If the die is bigger, the yield is lower. And I'll show you an example in a moment. The formula is the area is in the exponent in the formula, and we also have another element which is the fault density. So the number of defects per area times the area of the die. And that is very simple to understand when you think about it. If we have 1/10 of a particle per centimeter, and the die is 1/100th of a square centimeter size, then the probability of getting a particle is 1/1000, the multiplication of that. But if we have a defect density of 1 particles per square centimeter, and the die area is 4 centimeters, it means on average we have 4 particles on every die. The yield will be very close to 0, if not absolutely 0. Okay? So it's very clear that a bigger die will get more particles. Okay? So the bigger the die, the lower the yield, and the relationship is exponential. This is one of the reasons companies try to increase the yield very rapidly, increase the defect density, or reduce the defect density, increase the improvement in defect density very rapidly. Because the quicker you do that, the easier you can manufacture bigger chips. Okay? And bigger chips sell for more money, especially processors. Okay, if you have a bigger processor, it means that it has many, many more functions in it, and the customer will pay more for it. So this is an example to illustrate what I said before. Let's assume that we have the same amount of particles on two different wafers. Now, here, the technology is 2 nodes more advanced than this technology. And we can take the same die and print it in 1/4 the size. Okay, 2 generations more advanced. So we can get many, many more dies printed on the wafer. Yes?
Is it as the solution gets smaller, also smaller particles?
Yes, so that's true. If the technology gets more advanced, then smaller particles become killer particles. But let's assume for the moment we're talking about big particles, and we neglect the impact of having smaller dies with better technology. But if this is the case, what will happen is that for the larger dies, all the edge dies are not fully printed on the wafer. So obviously, if a part of the die is missing, the die is dead. So we get, out of 13 printed good dies, we get 9. Okay? So the yield is about a little less than 70%. While the same thing for a die which has 1/4 of the area gets us 94% yield. So, let's assume we're producing controller chips, okay? So maybe we can, with the same technology, have a controller which is bigger, but has more functions. But if the controller is 4 times bigger, the yield will be, look, 25% lower. So, and we would be able to produce much less wafers from the same die. So look at the amount of good wafers. Here we have 9 good wafers, and here we have 81 good wafers, 9 times more. So if we can save area in the design, if we can save area in manufacturing, we can make many, many more dies on a wafer. This is the driving force which is reflected in Moore's law, which I'll talk about at the end of the lesson today. Any questions? This is a real life example. And what we can see here is one wafer which all the edge is dead. Black means bad. This was dead by which operation? So EBR could be a bad resist on the edge, yes, but this is more than just one die at the edge. These are several dies at the edge. So one operation that impacts the edge more than others, actually most operations impact the edge more than the center, but one operation which is definitely impacting the edge more is polish. Polish at the edges is more sensitive. So I would guess this can be a polish effect. And we can see one wafer here, another wafer here, and another couple here. We can see other 2 wafers, this one and this one, with some systematic problem at the lower left side. So this could be, this one and this one. This could be another kind of problem. We can see on this wafer a line going from the top left to the right side. This line is probably a scratch. Something touched the wafer and killed all the dyes on its path. Okay? So, just a moment. Doing yield analysis, if you want to do it well, you need a very good eye. And when you look at the maps of the wafers, you get a lot of hints. And many times it helps you just from looking understand where is the problem. Was there a question? Because at the edge of the wafer, the polish pad gets... the edge is an area where the pressure is not continuous. The edge of the wafer is pressing harder than the center. In the center, all the areas next to the centers are similar. In the edge, on one side and on the other side, you might, if polish is not configured correctly, you might see a different pressure. And then the polish rate is different. And there's some other ways. Now, I'm not saying this has to be polished, but it might be. Okay. Now, the next sub-chapter is device and electronic testing, e-test. So we'll talk about the testing, the structures. We're checking resistors, capacitors, transistors, isolations, junctions, and many combinations of them. The electronic testing devices are small structures which are placed between the dies. If we make two dies, there's an area just between them, which eventually we saw with a saw, okay? And then this area is filled with many electronic structures which we can measure. Now, we don't want the competitors to get those structures. So actually, it's very good that we saw them later. So there's no trace of them, because from those structures, we can get the real properties of the different layers and so on. These structures are tested in several areas on the wafer. So if this is a wafer, we would measure a few structures in the center, a few structures in the edge, to be able to reflect all the area of the wafer. So resistors. We have wide resistors and we have narrow resistors. Here is two narrow resistors in parallel. So why do we measure wide resistors? What does it reflect? A wide resistor reflects the intrinsic property of the layer we're measuring. So if we're measuring a metal layer, the properties of the metal itself, taking into account its thickness. A narrow resistor reflects also the lithography results. So if we try to make the resistor as narrow as possible with the lithography, small variations in the lithography will be manifested in the resistance. Okay, so the wide resistors allow us to check the resistance and bypass the lithography effects. The narrow structures allow us to magnify the lithography effects. And the ratio between them allows us to isolate what is related to the layer itself and what is related to lithography. And I will not go through the equations of resistance, which you all know, and you also know square resistance, right? Because sometimes we're not interested in the resistance itself, but just the sheet resistance of the layer, which depends on the thickness. I'll skip that part. Okay. Contacts. The resistivity of the contact is very important. We want to make sure that the way we interface the transistors and other structures is not causing a voltage drop. So we can measure one contact, or we can measure a large number of contacts. You can see here a conductive layer here, a contact, a metal layer, a contact, conductive layer, contact, metal layer, contact, conductive layer, and so on. So we can get a chain of contacts. So when we measure one contact, we can check the contact resistance, and we can find if this one contact has a problem. Why do we want to measure a chain of contacts? The result would be very similar to measuring one contact, just doubled by 100 or 1,000. So why are we checking a chain of contacts?
The average power distribution?
So we get a better reflection of the average. If you measure one contact, you'll get a very large standard deviation. If you measure a chain, you get better reflection of the average. But let's assume, on top of that, what we're interested in is to find systematic issues, contact which are completely open. Now, not every contact will be open, but every 100th contact or every 100th contact will have a significant increase in resistance. So we will not be able to measure it when we measure one contact. But if we measure a chain of 1,000, it's enough that one contact is open, all the contact will be open. The resistance increase will reflect at all the chain resistance. So it allows us also to better find systematic problems of contacts. Okay. Capacitors. So we have several kinds of capacitors. We have area capacitors, diffusion edge capacitors, and poly-edge capacitors. So first, what are area capacitors? It's a big area, and the big area, we measure them one versus the other. So area capacitors we see in metals, where we want to check the thickness of the layer between the capacitors. Okay, the dielectric layer. We can check its qualities, its properties. Now, when the most important capacitor in the process, except for DRAM processes, is the gate capacitance, the capacitance of the transistor itself. Now, the transistor itself, we're interested in several things. First, the capacitance of the area itself to characterize the oxide. Then every transistor also has an edge with poly on top of it. So we're interested to see if there are any systematic issues with this edge. And then every transistor also has an edge with isolation structures. So we're interested to know the capacitance of that structure. So we make, this is an isolation, just like the one I showed you last time, an isolation trench filled with oxide. So we measure the capacitors, the blue is the oxide. So we measure the capacitors which have isolation edges. And this will tell us if there is a systematic problem in the edge with isolation. So the yellow will be, for example, a conductive layer, usually a polysilicon. Here we take structures which look like transistors, which don't have an isolation edge, but have an edge with poly. So if, for example, during poly etch, we do make a systematic issue at this edge, we will find it with this capacitor. So the different kind of capacitors allow us to differentiate between different problems in the process. I'll skip this. Transistors. So this is a schematic drawing of a transistor. And what do we measure for transistors? So we measure everything. Okay? We measure, you mentioned the VT. We measure the transconductance. We measure the drain current. We measure the breakdown voltage of the junctions. We measure the punch-through of the channel. And we measure the leakage current to the substrate. And nowadays, we also measure the leakage current through the gate. I know that you were taught that in a MOS transistor, the gate is not leaking. But that's in the old textbook. In reality, in these days, the gate is leaking as much as the leakage between the source and the drain. And the reason is that the gate is so thin that it becomes leaky. It's no more the thick gate oxide which is used for all the textbooks. Okay. Isolation structures. So here, if you remember, I showed you last time a trench which is filled with oxide, which was at the border between N-well and P-well. So here we have an N diffusion area in a P-well and a P diffusion area in an N-well. And we can measure the N-well to N diffusion or the P-well to P diffusion breakdown voltage. So this allows us to make sure that the breakdown voltage is high. Typical numbers is, say, 10 volts or 14 volts. Now, we do know that the transistors don't operate at such high voltages. So it means that even if the transistor operates, say, at 2 volts, okay, or 1.8 volts, then if the isolation structure breaks at 14 volts, there's no chance it will break at 1.8. But if the regular number is 14 volts and suddenly we measure a wafer and the value is 4 volts, 4 volts instead of 14. Even though the transistor operates at 1.8, we will say this wafer is problematic because it's different from the distribution of the other wafers. Something happened on this wafer. Either the trench is not in the right thickness or the doping is not the right doping. And this means that even if the breakdown voltage is 4 volts, there's a problem. And in some other areas, it might be smaller. There's a lot of variation, so it might get smaller, and we decide to throw this wafer away. Another isolation structure is in the same type of well. So between N plus to N plus in a P well or between P plus to P plus in an N well. And although in this drawing these two isolations look the same, in reality this one is significantly smaller than this one. Okay, less than half. Junctions. So same way as capacitors, we have area junctions and we have edge junctions, because in real life there are a lot of transistors which have edges, and we want to make sure there is no systematic problem with edges. Okay, any questions on electronic testing? So again, just to summarize, we have structures which are very simple. There are transistors or capacitors or resistors. They are placed in between the different dies, in the place between two adjacent dies. Later we saw this, so there's no mark left for production, for the product. And any variation on these electronic structures which exceeds what we call the control limits needs attention. If it exceeds what we call the dispo limit, we throw this away. The control limits allow us to find out any control issues in the line. For example, if a layer is too thin or too thick, and the dispo limits tells us that the actual value of this transistor or this resistor is too far away from what the designers wanted, so we decide to scrap the wafer, to throw it away, because we cannot guarantee the electronic performance of the chip itself. Before we go for a break, any questions? Okay, so let's continue. What we'll talk about now is assembly and then reliability. So what we do is we take the wafer. As an example, this wafer here, we dice it, and then we take the different dies out, and then the different dies are put onto a chip.
How do you sew it without vibrations or changing or stretching it physically?
So there are several kinds of sewing. The most advanced is using a wire coated with diamond particles. So, yeah. So what we do is we take the dies, we bond them onto a substrate, and then we cut those substrate, and they go into, if they're small, onto a small chip. If it's a processor, like this one is a Pentium 3, this is the processor, and we need a lot of pins out, so this is how it looks on the inside. This is when it's fully packaged in a ceramic layer.
So is it the flip chip?
I don't want to get into that. And then we have even bigger ones. And bigger ones, how do we cool them? We have a fan. Okay? Now, sometimes there's a very big chip which goes into a very small place. What is this? This is a discon key. Okay, this is the controller of the discon key. A very small chip on this side, and then the memory itself on this side. And you see almost half of this is just the metal connection to the discon key. Okay, so later in the break, I'll let you touch these. Sometimes the dies are very big and very complex. This is, before the Pentium 2, there was a Pentium Pro. Don't know if any of you heard of that. This is the processor, and these are two pieces of SRAM, big pieces of memory. And you can see that the design was too big to place on one chip. So this was very expensive. Now on the next generation of process, all of this was put into one chip. And then on the next generation, it was much, much smaller. Okay, so this is what we do in assembly. And then we also test the chips. We also test the chips when they are at the wafer level. We call that sort, or EWS, electronic wafer sort, or probe. It depends on the company. And there, a tester contacts the bond pads on the chip itself, puts voltages, measures the output signals, puts some data inside, checks that everything is okay. But the final testing is done at a chip level. Why isn't it good enough to test it on the wafer level? Because sometimes the problem will be created during the packaging. Now, in this case, why do we measure it on the wafer level? Why don't we measure only when it's packaged?
It's
Sorry?
Don't waste money on packaging when it's broken when it's done.
Exactly. So sometimes the whole wafer is zero yielding for some reason, and there's no point to put it in a package and to waste the money of the package. On top of that, and not least important, is the wafer level information we can get immediately when the wafer gets out of the fab. So if there is a problem, we can see it and correlate it not very immediately, but we can correlate it to the line, and we don't lose the information. If it takes another week or two to package it and test it, and we have a tool in the line which is performing badly, and we could have gotten the information 2 weeks earlier, it's a waste of time and a waste of a lot of money. So that's the reason we test both on wafer level and on die level. Yes?
Check the performance. You said you connect and you put the data. For every chip?
So we check every chip, but we don't check every chip for all its functionality. But we check several things for every chip. It depends what is the chip all about. For example, in some chips we do check speed if it's a processor. In some chips we check the leakage if it's important, if it goes into a mobile device which is sensitive to leakage current, which consumes battery. It depends what is the chip made to do. Okay.
Still, there might be some defects that you don't.
Yes. Some things we miss in testing. Yes. There are always testing holes. Okay. Now, failure mechanisms. So, let's assume we checked it. The chip looks well. We send it to the customer. The customer puts it in a computer, a controller, a cell phone, an iPad, or whatever. And then, after some time, it fails. What are the failure mechanisms and what are they caused from or by? So, first I want to distinguish between quality and reliability. If the problem is a test hole, and if we improve the testing, we can find the problem, it's a quality issue. Maybe the testing was not good enough. If it fails after some time, it is a reliability problem, if it fails at the customer's hands. So we have three regimes, three kinds of reliability failures. The first are infant mortality. For example, you buy a light bulb, you put it in, after a few seconds, it burns out. This is an infant mortality fail. It is called infant mortality because also for humans, babies when they're very, very young tend to die more than babies which are, say, a few months old. Okay? In the first few days, there's a lot of mortality. By the way, used to be, now it's less. But that's the origin of the name infant mortality. So this means that the light bulb had some problems during manufacturing which are gross problems, or that the baby had some serious, significant health issues and it couldn't live the first few days.
It's related to quality.
So we call it reliability because it does not fail exactly at the first time you turn something on. Okay? But it is very closely related to quality. So if we have infant mortality problems, we will also have a lot of quality problems that we can detect earlier. And that means that if a wafer is yielding low, it will probably also have reliability issues. So that's another good reason to scrap it, to throw it away. Even the good dies. Okay. The next fail mechanism is wear out. So if we take a light bulb, we plug it in and we use it after 2,000 or 3,000 or 4,000 hours, eventually it will burn out, okay? Because we wore it out. There was a failure mechanism that wears out the light bulb itself. For example, with a car, you have tires, you drive, eventually the tires wear out, and if you don't change them on time, they will break. Okay? So this is a wear out mechanism. The wear out happens on the other extreme of the infant mortality, at the end of the life of the part. And that is expected. It depends on the design of the part. For example, with a tire, the thickness of the tire, and it also depends on the way of use. If you have a computer and it's always on, it will wear out more rapidly than a computer which is turned on just once every week for a couple of hours. Okay? Yes, but if you turn it on rarely, okay.
But it's measured in thousands of years for nowadays processors?
So you will be surprised by, I'll give you an example. I bought a camera, a good camera from, I won't mention the company, a very good company. And after 2 years, it died. So I said, well, I had bad luck. I bought another camera from another very good company, not the same one. And after 3 years, it died. And I bought a camera for my daughter. After a year, it died. Okay? So if you take something and use it extensively, today's consumer electronics don't last long. Okay, for example, laptops, depending on the company, but on some companies, a quarter of, I won't say the company name, but a quarter of the laptops fail after the first 3 years. That's not what you would expect, right? But that happens. A good company, you get maybe less than 10% fail after the first 3 years. Okay. And then the last wear out mechanism is the random fail rate. And this happens from time to time for several reasons. As you can see, the fail rate initially is very high, then it drops. The random fail rate is very low, and then after a lot of time, we get into the wear out fail rate, which again is very high. So one way to make sure that you don't get a part with problems is to get a part that someone used for some time. Okay? And then you know it is already screened for infant mortality. So infant mortality relates to yield, okay, because it's related to quality. On the other hand, the wear-out regime is not related to yield. So this is related more to the design of the product itself. And the random is not related to yield usually. It's at a very low level. Questions? Okay. So how do we get that? What is the process mechanisms that generate these fails? So I drew here several lines and with several kinds of defects. Now, these are, let's assume, metal lines, and this is the insulation between the metal lines. Let's start with the very small defects. Is this defect a killer? Probably not. it's probably even not a reliability problem, because this particle is buried inside an insulator. Even if it's conductive, it doesn't matter. It's insulated, and it will not have any interaction with its surroundings. Is this particle a reliability problem? So, if it's a conductor, no. If it's an insulator, it consumes part of the metal line, so more current will flow through this part. But let's assume the part is well designed, so it can carry 30% more current without any significant problems. So if the particles are small enough, they will not a yield problem and not a reliability problem. Let's look at the other extreme, a large defect. So is this a yield problem? So if this is an insulator, then this line will stop conducting. So it will be a yield problem. If it's a conductor, these two lines will be shorted. So it is a yield problem. But it will not be a reliability problem. It is a quality problem, not a reliability problem. Let's look at this part. Will it be a yield or reliability problem? Probably not. Okay? What about this one? So if it's a conductor, it will not be a problem. If it's an insulator, still half the line is conducting. So it will probably still not be a reliability problem. What about this one? If it's an insulator, it will not be a problem. If it's a conductor, then here the distance is very small, too small. Depending on the signal, on the voltages, it might short. Okay? And in that case, it might become a reliability problem. What about this one? Quality or reliability? So quality, if this is a conducting part. Okay. What about if this is made of polysilicon? So if it's polysilicon, it might conduct or not conduct depending on the temperature and on other features. So it could probably be a reliability issue, because sometimes it will conduct and sometimes it will not conduct. Usually not when you want it. Okay, it will do the opposite of what you want. That's Murphy's law. Okay, so this is the relationship between particles and reliability.
Every process has a particle inside, or?
So not every chip has particles inside. There are chips which have no particles at all, zero. The smaller the die, the more probability you will see such chips. Another reliability mechanism is a wear-out mechanism called electromigration. Now, Yossi did a lot of research in this. He has lots of leading articles. He's a well-known scientist in this field. So what is electromigration? Apparently, the flow of electrons is not harmless to the metal line. The electrons hit the atoms, and although they have very small impact, eventually they can move the atoms. Okay? Like water dripping on a stone, eventually it will make a hole through the stone. So the metal line is formed by several crystals. And what happens is that the current goes through the crystals and also through the interface. And sometimes more current flows through the interface. And what might happen is that we have voids in the metal and voids also in the interface between the grains. And we might get accumulation of the voids in the grain boundaries. So the blue lines will be grains. Eventually, they might not conduct current. And what happens is that these voids might grow and the grains will become smaller. And eventually, what happens is the metal line itself becomes non-conductive. Instead of having a small void, we get a big void. And then the line itself becomes an open line instead of a conductive line. So think of the atoms as big rocks, and think of the electrons as water molecules in a stream. And then the stream of water eventually can move the rocks. And what happens is that the electrons can move the usually aluminum atoms and to produce a situation where there is no more current. Now, let's assume this part of the aluminum is removed. Then on the remaining part, we will have more current, so more flow. And then the probability then that the next part will be removed is greater. And then we will have a smaller conduction line. And then the current will increase there until we get a very thin line like a fuse, and it fuses, and there's no more conduction. That is electromigration. How can we avoid electromigration? So just the same analogy of the stream of water and the stones. First, put bigger stones. So instead of aluminum, we can use copper. Okay? And then another way is to make shunt layers. Make a shunt layer from tungsten, for example, that goes at the top and the bottom or on the sides. And even if there's no aluminum or there's no copper, it allows the current to flow on the sides and it will not fuse. Okay? So these are the most usual ways to tackle electromigration. Any questions?
It gets worse when the frequency gets higher, right?
It's not that simple. I rather not get to the frequency dependence. Okay. So now the next chapter is the connection between the process and the design, the layout. Very, very briefly, I know you study a lot of this, so I'll just mention we have a logic design through a RTL. We get modules, for example, a register or a memory unit. Then we have a synthesis. We get a scheme, for example, this one, what's this? An inverter, okay? And then there's some automatic tools that puts it on a layout, okay? You have a lot of courses about that. I don't want to get into that. Okay, okay. So, anyone? What's RTL? Do you remember? No. Okay. So what I want to focus on is this area where the different colors are different layers in the process. So what we do is we take, for example, if we want to take a processor, the processor is made of certain parts, and those parts are translated into more basic parts like NAND gates, NOR gates, and so on. And then those are translated into layout, which, where is the layout? How does the layout get into the wafer? Through what? Through lithography, through the mask. Okay. So this is an example. What we see from above on the layout is a green area, a green rectangle, and then a red rectangle on top of it. The red is the gate, and the green is the active area, which consists of the source and drain. Okay, so this is just the transistor. Later we have more and more layers. We'll start with just 2 layers. Okay, so this cross eventually is a transistor. Okay? Now, since you wanted to see something more complex, this is an inverter. So, this is the scheme of the inverter, the P-channel transistors, the N-channel transistors. Here we have the ground connections. Here we have VCC. This is where the signal gets in, and this is where the signal gets out. So, when the signal gets in, where does it go to? The gate. So let's check the layout. This green part is metal 1, the first metal layer. So this is the input. The blue is the contact. Contact, so this is the metal in the cross section, and the blue is the contact. You can see this B cross section is this one, and this A cross section is this one. Okay, so now we understand the green part. This is the metal, and here is the contact. The contact gets into this red line. What is this red line? This will eventually be the gate. This is the polysilicon. Here it's not the gate yet, but we can see the red line goes here and here. In this area, it's on top of isolation. So the poly serves just as a line, just as a link, okay, a conduction line. Here, this is the P-well, this area, this light blue. It's the P-well area, and in the P-well area, this would be an N-channel transistor. Okay, so this is the gate of the N-channel transistor, this gate here. And on the other side of the red line, we see the P-channel transistor. Okay? And this magenta color is the N-well. And in this area, in the N-well, we have the P-channel transistor, which is this gate here. Okay. Now let's look at this connection between the drains of the 2 transistors. So we can see the drain of one transistor here. You can see it here, right? The drain of the other transistor is here. This is this purple area, and this was the light blue area, and they're connected through this metal line here, this metal line, which is the output voltage. Okay? And what we can see more is that we have a P plus on N-well. This would be the P-channel transistor. N plus on P-well. Actually, in this inverter, we don't have a P-well because all the substrate is P. So we saved one layer. So this is the substrate, and the P substrate will get an N-channel transistor. So this was this cross-section. On the other cross-section, what we see is this connection and this connection. Okay, this contact and this contact. We have P plus connected to the substrate. So what is this? No. So this is in order to control the body of this transistor. Okay, in order to control the substrate voltage. Okay, and this one, N plus to N well, it's an ohmic contact. This is in order to control the body of this transistor. Okay, so now you saw how we took an inverter, we put it into transistors, and we made the layout. Okay? And later, depending if we have time or not, I will go through the processing here. So you will see a two-dimensional processing on top of what I showed last time. Actually, this is three-dimensional. Last time was two-dimensional. Yes? Why there are two connections? Okay, so the question should be, why is the P-channel transistor wider than the N-channel transistor? So you should be able to answer that. The difference in mobility. So the mobility of the holes is smaller than the mobility of the electrons. So if we want to get the same order of magnitude of current, we need the transistor to be wider. Okay. Still, why do we need two contacts? Why not one? One will do the same work. The current will be uniform enough. That's not the... What? Redundancy. What does that mean? So, we just talked about yield earlier, right? So let's assume one of these contacts is blocked. If one of the contacts is blocked, still the other contact will be there and the transistor will operate normally. So we have the second contact as a redundant contact to the first contact. So wherever we can, we try to put more contacts, okay, and not to save in contacts. Yes?
If you take the entire substrate as P, and
Yes.
you add more donors to make the N well, isn't it destroys the mobility of the channel because you have more...
So the mobility depends... the mobility depends on there are several kinds of mechanisms, which I will not get into, but the overall doping, the overall amount of dopants is related, or the mobility is related to the overall amount of dopants. But when you look at the actual values, if you want to have an N-well here, the substrate could be 10 to the 15 per square centimeter, and the N-well can be 10 to the 17, and then the P plus can be 10 to the 19. So if the mobility here is determined by this 10 to the 17, even if you add 10 to the 15, it's completely negligible, and it will not impact the mobility. Okay? By the way, there are other mechanisms that determine the mobility, which are mentioned in other courses, semiconductor physics, for example. Okay. Any more questions about the inverter? So I will skip some of these foils. You all know what's an inverter and how does it work, and where the voltage switch is, and that if we put a high voltage, we get a 0, and if we put a zero voltage, then the NMOS is not conducting, and then we get the output voltage is VCC. Okay, so you all know that. I want to mention that in other courses you saw that with the same kind of logic we can produce a NAND gate and many other things. By the way, why do we prefer doing this with a MOS transistor and not with a bipolar transistor, for example? Yes, so let me just show you here. What we can see is that in any case, one of these transistors is not conducting. So in standby mode, when the inverter is not switching, we will have zero current because one of the transistors will be shut off. By the way, it's not really zero because there's leakage, but all the power consumption will be done during switching, and there will be no or almost no power consumption during standby. So this is the reason CMOS was able to be the prominent technology. Okay? Now, excuse me for the noise. Okay. We can also do NOR gates, and the difference between the NOR and the NAND is just the different ways we organize the N channel versus the P channel transistors. What's the function of this layout? Which one? Good question. So let's start with the left one. So in order for the so you can see that the N channels are in a serial and the P channel are in parallel, and here it's the opposite, right? So one would be the opposite of the other, and instead of guessing, we will see that NOR has the N channel transistors in parallel. So this is NOR and this is NAND, and you were right. Okay, so looking at the layout will help you understand what are we dealing with. Okay, NAND and NOR. This is a more complex layout of an SRAM. I will not get into all the details. But we can see here that we have 6 transistors. 1, 2, 3, 4, 5, 6. The pull up and pull down and the memory element. Okay, I will skip how this operates and the timing elements. And now I want to show you the process of making a NOR, the process of making an inverter. And we will do that after the break. So let's get back here in 10 minutes. Thank you. Okay, let's continue. So now we'll draw the layout of an inverter, which is a NOT gate. Okay. First, we'll define the active areas and the isolation areas that will define the transistor width. So here, we'll take a mask. The mask will look like this. And here, the mask will have chrome to cover the areas. And then we'll put resist on the wafer, and we'll expose through the mask. The areas covered here with chrome will not get exposed, and the areas that will get exposed will eventually develop, okay, and go away. That is positive resist. Okay, after that, what we'll do, and let's look, for example, at this rectangle, which eventually be the p-channel transistors. Now it's the N-well. The area is protected, okay? Here, the area between the N-well and the P-well is not protected. There will be no resist here. And we will be able to do the following. We will be able to etch the silicon. How do we etch the silicon? Dry etch. What would be the first step? Breakthrough etch, right? And then the next step will be fast etch. It will be some kind of silicon etch. And how will we know when to stop? We don't have an endpoint because we're etching into silicon time-based, okay? And the thickness, the depth will be about 0.5 micron, okay? The thickness of the isolation depends on what we want to get, but 0.5 micron is a typical value. Okay. So we will get active area here, isolation, active area. On the other side, where we want to contact the substrate and contact the N-well, we will get most of the area is isolation, and only here and here there will be active areas where we'll eventually get the contacts. Okay. What would be the next step? By the way, STR means shallow trench. Okay, shallow because in other processes, for example, DRAM, there used to be deep trenches. So this is called shallow trench. Then we will take a mask where chrome covers all this part, and we want to open this part. Now we will define the N-well. Okay? What we will do is we will spin resist. We'll expose the resist through this mask. This area, the N-well, will get light, right? All this area will be developed. It means positive resist. And after it gets developed, what will happen? We want this to be an N-well, so before we remove the resist, what we do? We implant. The energy of the implant will be selected to be able to get the depth we want. Say about 1 micron in this case. Okay? And the amount of dopants will be determined by the dose of the implant. Okay, so the dose and the depth determine the doping level. Again, it will have to get annealing, but after annealing, it will determine the doping level.
You have two levels. Half a micron of difference, and you put it to a depth of 1 micron.
Yes.
How do you differentiate? Because of the
So how do I differentiate between?
Because you put 1 micron in, right?
Yes.
So the heel is half a micron.
Okay. So what I didn't mention, and I didn't do it properly, so I'll do it again. Here, after we etched the trench, we fill this with SiO2. We fill this with an isolation material, and then we made it smooth. How did we make it smooth? With polish. Now, how did we know where to stop? So here we can get an endpoint. So the real process has a nitride layer that helps us to endpoint. And the way the endpoint is done, this is a polish pad. And the wafer, I won't take it out, but the wafer polishes over the pad, okay? And then you can see there's a window in the pad. And something sticks out of the window. A laser. The laser gets reflected from the wafer when the wafer gets on top of it. And then there's a detector that measures the also the phase of the laser that gets in. So knowing the phase of the laser that gets in, we know first from the intensity we know what is the reflectivity of the layer and did we reach a layer which is reflecting less or more. But we can also determine from the phase what is the thickness of the remaining layer. So we can actually polish and know before we endpoint if we're getting close to endpoint. So this is a real pad and a real window. The laser is used is different. Okay. Why do we polish before we move to the next step? One of the reasons is when we do lithography, we want everything to be smooth. And also later we will build layers and layers and layers, so it's better to build on smooth. One other question I have is, what is the resolution we need here? So say if this is half a micron, this is also half a micron. So the resolution we need is about half a micron. This can be done with an I-line tool. It can be done better with the deep UV tool, and with the 193 nanometer or with immersion tools it can be done much, much easier. So which tool will we choose? The cheapest one. Which would be the cheapest one? The I-line, the 365, thank you. So we will choose the cheapest tool, and the cheapest tool would be the one with the worst resolution. So for each layer we will choose the worst resolution that will still work. Okay, so which resolution will we choose here? This is several microns across. So still, we can do it with visible light, but we will still use I-line. There's no tool with visible light anymore in the fabrication facilities. Okay, so we said we will implant. Now, I show here that the implant depth is pretty much the same below the active area and below the isolation. The reason for that is that the stopping power of silicon dioxide is pretty similar to the stopping power of silicon. Not exactly the same, but pretty similar. Okay, what will we do next? Next, we will do the polylines. So obviously, we skipped a few steps. We need to remove the resist. We'll do that with ashing and then wet cleans, usually sulfuric. And then, before depositing the gate, we need the gate oxide, right? So we'll oxidize the gate oxide. We'll get the gate oxide over all the wafer. Then we will deposit a polysilicon layer, which is the red material. Then we will pattern the polysilicon layer. And this is actually thicker than it looks. Usually, this is the minimal dimension of the process. Why is the poly width the minimal dimension in the process? This would be the width of the channel of the transistors. So this will determine the speed of the transistors. So here we will use the best lithography tool we have in order to achieve the best speed for the transistors, assuming we want speed in this case. And if this is a microprocessor, we probably do want speed. So we grew the oxide, we deposited the polysilicon layer, which is the red one, and then we use this mask. We protect this area with chrome, positive resist, we develop all the rest, and then we take it into an etcher. Which etch will we use? dry etch. Dry etch, wet etch will probably undercut below the resist, and this is a very critical dimension. We don't want it to be messed up. Okay, so we'll use dry etch. What steps will we use? The first one will be breakthrough etch. The next one will be, we want to etch silicon, okay? Silicon etch, either a fast etch or not a fast etch. Then we're getting close to the, what do we have below the silicon? The oxide, the gate. Okay, so we have the gate on the active areas and we have oxide on the isolation areas. So we will use an etch which is selective, so it etches silicon and it does not etch oxide. Okay? And then what happens if that etch will suddenly etch oxide? We will punch through the thin gate oxide and we will start etching the silicon of the wafer itself. So it's very critical in this step to have an oxide which is selective. So we will etch with the selective etch. What will we do then? How will we know when to stop? So either with timed etch or with endpoint. Endpoint is obviously better. And then what will we do? An over etch, potentially even more selective, because we want to harm less the oxide, which is the stopping layer, and it's usually a very thin layer. Okay. And then after we do that, what will we do? Then we want to etch the oxide, because later we want to have contacts in here. We want to contact the silicon. So then we will etch the very thin gate oxide layer with an oxide etch. Okay? Again, we want this oxide etch to be selective in order not to etch the silicon below. And we can use an endpoint, a selective etch with an endpoint and an over etch. Okay. Why do we need the over etch? We need the over etch to make sure that the oxide is not removed only from this area here on this specific die on the center of the wafer, but also in the edge dies where the etch rate is different, so we might have etched less, and also in areas in the wafer where the structures or maybe the polylines are more dense and the etch rate between them is lower. Okay. Any questions about this?
What's the thickness of the seam between the polygate and the...
So it depends on the voltages we want to operate. Say for a 2-volt operation, it's roughly 20 angstroms, okay, which is the physical thickness. Next, we want to make the P+ contact. So the P+ will be the source and the drain, and will also be the contact to the substrate. So we take a layer, we take a mask, we spin on a resist. Now we use, in this case, we use a negative resist because the, positive resist. The areas here are areas which we want to keep open. And then we implant. We see the implant penetrating the source and drain. It also penetrates the poly here. It will also penetrate this area, which we can see here. Now, the poly will have partly will be partly implanted by P-type, partly implanted by N-type, and in some areas might not get implanted at all. And what we need to do is to eventually salicide it, have a layer on top of it that will allow a conduction between the N and P areas. Next, in the same way, we implant the source and drain of the N-channel transistor and also the contact to the N-well. Any questions about that? Now, after that, we remove the resist And when we remove the resist, this is the time after we finish all the implants that we do the anneal. We rather do the anneal only once. We can do the anneal several times in the process, after the N well, after the P plus, and after the N plus. Why do we want to do it once only after everything? So one reason is not to do it 3 times, because each time will further diffuse the previous implanted layers. And the other thing is money. We don't want to waste money. If we can do something once instead of 3 times, we'll do it once. Okay? Next, we will deposit silicon dioxide with probably plasma CVD. After that, we will use a litho layer with holes for contacts. And what lithography will we use? Look at the dimensions of the contacts. The contacts are usually pretty small. So again, we will use the best lithography tools we have, depending on the availability, on the process, and on the design. Why don't we use bigger contacts? You know, bigger contacts are better. They're less conductive. Why don't we use bigger contacts? It consumes silicon area, and then it means the product will be bigger. I can tell you that in a contact of a process which is 3 generations old, today we put all the transistor, sometimes even more than one, in the area that previously we put 1 contact. And the contacts today are more resistive, but they're much smaller. So we will try to use space, and we'll use the best lithography we have. The etch will be a dry etch, and we want the etch to be very selective, to consume oxide, but not to consume silicon, especially since some of the contacts are deep and some of the contacts are shallower because they need to contact poly. Okay, so you see that we will open, let's see, 9 contacts. Okay, 6 of them for the transistors and 2 for the wells and 1 for the poly itself. This contact will eventually be the V-in, the input. Next, we will do the metal 1 layer, and again, I don't want to get into too many details. We can do it either with the damascene process, like we do copper, or with the etch, like we do for aluminum. But eventually, we'll get the metal 1 contacts, and we'll see the inverter that we investigated initially. Okay, so this is the process of producing an inverter. And as you saw, where we can make an inverter the same way we could have done a NAND gate or a NOR gate, depending on how many transistors and the connections. So with the same kind of process, we can do any structure, any gate we need, a NAND, a NOR, a NOT. We can do an inverter. We can do several other structures. Okay. Any questions about the process? I did it in a much quicker way than last time, just to show you that we have a 3-dimensional process, and that eventually, looking at the different colors, you can say what does the layout mean. So this is an inverter. Now we'll move into future trends. So this part of the foils are foils which I need to update every year, because every year what used to be the future is not the future anymore, is the present. But some things stay the same. So we'll start with Moore's law, and then we'll go into more details. Also, I'll give you some historical perspective. So this is the original drawing of Moore's law. And what you wrote here is the relative manufacturing cost per component. So this is the cost. And here is the number of components per integrated circuit. So in 1965, Gordon Moore, which was one of the three founders of Intel, predicted that every 2 years, the number of transistors in a chip will double. Eventually, it was a bit wrong. It didn't take 24 months. It takes 18 months to double. And what he shows is that the minimum cost per component from 62 to 65, and this was done in 65, gets lower, and he predicted that in 70 it will be here. And the minimum cost per component eventually determines how many components we put in a chip, because this is here we can see that the minimum correlates to the number of components, and we can see that at 62 it was very close to 10, the optimal point. In 65 it was closer to 100, and he predicted that in 70 it will be closer to 1,000. Okay? So he predicted the exponential growth rate of the number of components, let's say the number of transistors in a chip. That is Moore's law. This is, by the way, the original foil. And this is a graph presented by Gordon Moore himself a few years ago. And what we can see is this is the log scale, the number of transistors per die, the numbers of components per die. And this is the year. We can see the actual data he had on 1965, from which he extrapolated the law. And we can see the trend. Now, the yellow triangles are processors by Intel. And you can see that Pentium 2 wasn't a good processor because it had less transistors than what expected. On the other hand, the move from Pentium 4 to Itanium was a bit better. Okay? You can see memory, and it doesn't matter if it's NAND or DRAM. In this case, it was DRAM. And you can see by the way, now at 2010, we're more than 4 gig. We're almost 16 gig. And this was his original projection. Okay. What we can see is that the number of components double themselves. What is the reason for this doubling? What is the driving force? So the demand is always there, but the demand doesn't let you double. What is the technology element that allows you to double the number of transistors? The advances we have in lithography, in the resolution. So there is an expectation from the industry to the manufacturers of lithography tools to be able to produce every 18 months a lithography tool which enables to shrink the line by 0.7, a factor of 0.7. So the area shrinks by a factor of 2. Okay? So every year and a half, we get a shrinkage of the area by a factor of 2. And this is actual data, pretty impressive. And take into account that the prediction was done at 65. Now you can understand why he's one of the very successful managers of the industry. Okay, also one of the richest person in the world, and I want to add that he contributed most of his money to charity. Okay. So modern technology features. Right now, 300 millimeter wafers. Sometimes moving to 450. We have 9+ layers of metal. Every year I update these foils. We have more layers of metal. The pitch, the line and space, I wrote here, smaller than 100 nanometers. So now the number is significantly smaller. Now the half pitch in production is 22 nanometers of the most advanced processes. Okay? The aspect ratio, which is the ratio between the depth of a contact and the size of the opening at the top, moved from 6 to 10, and now some of the aspect ratios are even higher than 10. So the contact is, if this is 1, the depth is more than 10. Tri-gate, I will talk about tri-gate. There's, I believe, at the moment only one company selling this commercially. Would you like to guess who? Yes. Strained silicon. So in order to make the transistors faster, we make the distance between the source and the drain smaller. But on top of that, there's something else we can control. What can we control? The mobility. So we strain or stress the silicon to better control the mobility of the electrons. And by the way, electrons and holes react differently. So one of them we need to strain, the other one we need to stress.
Depends also on the directions of silicon.
Yes, okay. The technology is fully planarized. I think there's a spelling mistake here. And in the past, some of the processes did not have a planar every few steps. Now every process has planar in every few steps, or else litho cannot get the right focus and get the right resolution. Sally-sided gates. Today, actually, some of the gates are not sally-sided, but some of the gates, instead of oxide gates, are metal gates. Speed, much above 2 gigahertz. So this trend didn't move as fast as the others, and it got stuck at about 4 gigahertz. And there are a lot of state-of-the-art processors which run at about 2 gigahertz. Why did it stop? Do you know? So when we increase the frequency, the heat dissipation increases. And what happened is that we make the transistors smaller, we put more transistors, we increase the frequency, and we get more heat in a much smaller area. And if this trend would to continue, we would get, in a few years, an area which is hotter than the exhaust of a jet plane, and later hotter than the sun. So obviously this trend had to stop. High K gates. So high K gates is what I mentioned as metal gates, where the gate is not, the oxide is not made anymore of oxide, but actually of some kind of metal gate, which is not conductive. And the high K means that we get a higher dielectric constant. Okay, we need a higher dielectric constant because then we can get, with a thicker gate, we can get the performance of a thinner gate. Quite the opposite for the ILD, interlayer dielectrics, the layers which are insulating between one metal layer and the other. Okay, and obviously, we want to have better insulation. That means a lower dielectric constant. And as I said, there are many ways to do it. One of them, for example, is producing a material which has air bubbles inside, because air is the best, has the lowest K. And yes?
What is IMD?
Interlayer dielectric. The dielectric you put between two metal layers.
To reduce the capacitance?
Exactly, to reduce the capacitance between the metal layers.
And why do we want high K for the gate?
For the gate, because we want the gate to be as thin as possible. And if you get high dielectric constant, you can physically use a thicker gate, which performs like a thinner gate. A thinner gate is very difficult to control, very difficult to produce. Okay? And there are also tunneling effects when the physical thickness is smaller. Thank you. Okay, what I didn't mention here, now we're getting close to three-dimensional structures. And the three-dimensional structures usually for memories, not for processors. Okay. So let's see it. So what you can see here is a picture of tunneling electron microscope. So what you can see here, every dot is an atom. Did you ever see atoms before? So is this really one atom? No, it's not really one atom. Actually, this is a crystal, and there's a line of atoms behind it. So we see it as one atom, but it's really several hundreds of atoms, one behind the other. Okay? We cannot see one atom yet. And what we can see here is at the generation of a 90 nanometer process, which we had at 1995, 1994. 2005, 2004. We had a silicon oxide gate of 12 angstroms. And now we can get a thicker gate, thicker physically, which performs better than this thin gate because the fact that it has high K. Okay. On top of that, the leakage is significantly smaller. Why is the leakage important? Static power dissipation. And actually, today, the thickness is not 30 angstrom. It's much smaller than that. So it is really important. And today, the leakage through the gate is very close to the leakage between source and drain. Okay. Next is strained silicon. So what we can see here at the bottom is an effect where the silicon is being strained or stressed by some capping of the transistor with different layers. So the different layers stress it or strain it. And we use silicon nitride or some other things. We also use source and drain from silicon germanium. Okay, this allows us to control the stress or the strain because silicon germanium has a different lattice constant. The cell size is bigger than silicon itself. Dislocations, of course, it actually happens, and we need to have a very good process to avoid it. One of the ways to avoid it is to do it on thin layers, so the stress doesn't have to release itself through dislocations. Yes. Okay. Another thing which at the time, this again is taken from Gordon Moore's lecture, at the time was a drawing, and later Intel published this picture you can see of the gate, and this is the source and drain. This is a tiny silicon line, and instead of having the gate control it only from the top, it controls it also from the two sides. Like here, this is the gate, and it controls the silicon also from this side and from the other side here. So we actually can shut the leakage better, because we shut it not only from the top but also from the sides. Okay? Today Intel has a commercial process that has this available. So what Gordon Moore said at 2005 is actually on production now. Well, he knew what he was talking about clearly. Okay. So we mentioned that we doubled the density by a factor of the square root of 1 over the square root of 2 every 18 months. And we don't know what will happen next. This is what Gordon Moore said, that the space between generations will grow instead of 18 months. I can say that today we are at 22 nanometers in production. So it moved even, it answered his question mark. He was sure about 30 nanometers, but not sure about the next step. Technology challenges, speed and small size, submicron lithography. So we had the extreme UV and immersion tools. Immersion tools are actually in production for several years. X-ray lithography, still not in production. Phase shift masks, I don't know if you learned that. It's in production. Stress and strain silicon are in production. Speed RC effect, low K ILD is in production. Copper is in production for many years. Super shallow junctions are in production, and epi growth on source drain is in production. So most of the things which were thought to be future trends are actually running. High aspect ratios, I mentioned, are something that are being done today. And now some historic perspective. So this is the first computer produced in 1946. It was called the ENIAC. And it has a lot of light bulbs, like those were bulbs before we had transistors. Vacuum tubes, small vacuum tubes. By the way, do you know why a bug is called a bug in programming?
Because the first bug was bug.
So when the instructions didn't work well, the program didn't work well on this computer, usually they went and checked all the vacuum tubes, and they found a bug, a physical bug, a beetle or some other bug, that electrified itself between the two contacts of a vacuum tube, and that is actually what hurt the calculation. So that was the reason a problem is called a bug. This is the source. So just to compare, I compared this, I didn't update this for a couple of years. I compared the ENIAC to a laptop from 2008 with an Atom processor. Now there are much better processors. It had 18,000 tubes versus more than 2 billion transistors. The memory was 200 bytes of RAM versus over 2 billion bytes of RAM. It could do 5,000 additions per second versus more than 50 billion additions per second. MTBF is mean time between failures. Every few minutes it used to fail. Now, at least for the processor, it fails over several years. It weighed 30 tons versus my laptop 3.5 kilos. So this is the progress which was done over, let's see, from a little more than 50 years, 54 years. Okay? And 64, let's see, 56 years. No, let's see. 46 years, less than 50 years. So this is the progress that was done, and it's amazing. Think of it. No other industry, no other technology improved this much, even in 50 years. Not even nuclear science. So we have these tiny vacuum tubes. More than 2 billion of them are in one chip. Actually, today we have more than 16 million of them. This is the first integrated circuit made in 1961. Look at it. Look how dirty it is. Look. No one would like to sell anything like this today. This was the beginning. This worked. And look at what we have today. Impressive. Now, it is very difficult to predict what the future will look like. I want to read to you two quotes. So Ken Olson, the president and CEO and founder of Digital. Did you ever hear of a company called Digital? So it was the number 2 computer company after IBM. And it disappeared. Now, the Ken Olson, the founder, said in 1977, "I don't see any reason that someone will want a computer in his house." That was said by a leading person in the industry in 1977. So now you can guess why Digital disappeared. Now they left home computing for other companies, mainly IBM, that conquered the market and made Digital's business obsolete. And then Thomas Watson, which was the chairman of IBM, said in 1943, "I believe there is place in the world market for only 5 computers." And again, he was a great man. He led IBM to great success, and IBM eventually became the leader in home PCs, right? We call it IBM PC, even though IBM does not produce PCs anymore. So the lesson we need to learn is the future develops much faster than we know. It is very difficult to predict. And there are very, very few people in the industry like Gordon Moore, who in 1965 predicted the progress for many, many years. So I'm done. Any questions? So if you'd like to stay and see some of the things, you're welcome. And if not, thank you. It was my pleasure.